So we're now looking at the outputs of linear systems when the inputs are random processes, and we're looking at it over all time. And in the previous video, we derived these three formulas, you could call them, for the mean, the autocorrelation function, and mean square of the output. I did a couple of examples. I'm going to do another one. Here's the example. It's this first order system where the input is just, its power spectral density is just a constant, meaning it's white noise with amplitude A. And our job is to find the mean and the mean square value. And then the mean square value as time goes to infinity. The mean is easy because if the input mean is 0, the output mean is 0. You know, if you go back to that formula for the mean, it doesn't matter what this integral is. If the expected value of the input is 0, you're going to get 0. So, and since this does not have a Dirac delta function in the power spectral density, its mean is 0. So the mean is easy. So let's do the mean square. So here's the transfer function. Use the Laplace table to find the weighting function, and here's the weighting function. We're going to need the autocorrelation function, so we take the inverse Fourier transform of the power spectral density, and it is a Dirac delta function. Here's the formula for the mean square. Here's what it is when you plug in all that stuff. So here's the integral you need to take. Here's where I don't want to go through this too fast. We have integrals involving Dirac delta function. This is one of the more difficult little subjects in this whole module. So it's worth going over this slowly. Maybe too slowly, but it takes some. You got to know what you're doing when you do this. We're going to use what's called the sifting property of the Dirac delta function. What does that mean? Let's say this inner integral is over u, right? The way it's written here. And by the way, in this case, here's the region of integration in the u-v plane, which are variables of integration. They both just go up to t, right? Same t. So it's a square. The sifting property says whatever variable of integration makes this argument of the Dirac delta function be 0, you plug that into what's outside the Dirac delta function. So here, integral of integration on the inner integral is u. So what makes that argument 0? When u equals v. So we would plug in u for v, or excuse me, v for u, and that's what evaluates to this inner integral. Right, so this u plus v just becomes 2v. Then I'm left with the outer integral. You know, it doesn't matter if I'm integrating over u first, so I'm going over that way. So I'm guaranteed to encounter that line where u equals v for no matter what v I pick or what u I pick. So I was good over that interval of this integral. So now I take the other integral the way I normally would, and end up with this for the mean square value. Out as time goes to infinity, this part goes to 0, and I'm just left with a over 2t. I think I did this in steady state analysis, came up with the same answer. Now we do it by finding the answer for all time and then taking the limit this time. I'm only worried about as time goes to infinity. you know, do steady state analysis. This is going to be a long video probably, because I want to get into these integrals with impulses. Here's that sifting property. Variable of integration is tau. Whatever tau makes this argument 0, you plug it in there, and that's what the integral evaluates to. G of t. Tau equals t is where this argument is 0. If this function is just 1, or the integral of the Dirac delta function itself is just 1. These limits have to be enough, though. What if I had this? Now I've got limits on the integral, 0 to t. This is only going to be 0 when tau is between 0 and t. Otherwise, I'm going to get 0. So it's only that sifting property is kind of tricky in this case. Depends on the limits of your integral. Here's maybe a tougher case. Now where tau equals t2 minus t1, that's where you would evaluate this guy at tau equals t2 minus t1. But your t2 minus t1 has to be in these limits, or t2 minus t1 is between 0 and t2. Otherwise, you get a 0. I could rewrite this by it's the same as this. I'm going to keep going. This is going to be a long video. And we've actually done this before. The transfer function or your system is a simple integrator, which means your weighting function is just 1, and your input is white noise. We're going to integrate white noise. Find the autocorrelation function. Well, from the formula we had, here's the formula. Our G is now just 1, so these are just 1. And let's see. We're just left with this guy, which is a Dirac delta function. This is the argument. So here's the integral we need to take. Here's the integral we need to take. And I could do either over u first or over v first. T1 is associated with u and T2 is associated with v. So if I change the order of integration, I have to change these limits as well. Let's look at the region of integration. If T2 is greater than T1, it's this tall rectangle. If T2 is less than T1, it's this more horizontal rectangle. And this is the line where the argument equals 0. You can sort of solve this for V. And you get that line. Now we want the trick into evaluating these is which variable do you integrate over first? If I tried to integrate over u first with this tall rectangle, I'd have to break it up. I'd get a different answer down here than I would up here. In fact, I'd get zeros down here. And I'd have to figure out where this point is. But if I integrate over v first, I'm guaranteed to cross this line where this argument is 0 exactly once. And I don't have to worry about what u I get. Just integrate over v first if this is the case. In this case, I want to integrate over u first. Then I don't care what v I get. I'll cross that line exactly once. That makes the inner integral easy to take. T2 is greater than T1. I'm over here. I integrate over v first, so I integrate. That inner integral is just 1. And all that's left is I'm just integrating over u from 0 to t1. And I get t1. T2 is less than, I'm integrating over u first, this way. That inner integral is just 1. The outer integral is just 1 from 0 to t2. I have these two simple answers, and here is the overall answer. The autocorrelation function is just the minimum of the 2 times. We did this when we derived or explained the Wiener process. Sorry it took a while. I'll do this other example in another video. But you just have to be careful, and it's going to take some time if you have to do this kind of thing yourself. It's going to take some time to get into it and do it right. You don't need to know it. You can skip all this.